Hello, my name is Ana Navarro, and today we'll be going over integrating drone technology for precision agriculture. I am a senior at Texas A&M University Kingsville, graduating in the fall of 2025, and my major is agriculture science with a minor in agribusiness. So to start off with the executive summary, drones offer real-time data collection and precision farming capabilities. The key outcomes are increased crop yields, reduced input costs, as well as better resource use. This report explores applications and future directions. Some of the main benefits of drone technology in farming include improved crop monitoring, efficient input application, reduced environmental impact, and enhanced data analysis. Drones also allow the early detection of issues and produce high-resolution images and data that reveals subtle crop changes, allowing us to start off with precision spraying drones that can apply pesticides. So for our introduction, agricultural challenges in the modern era, climate, efficiency, sustainability. What is precision agriculture? Precision agriculture applies tech to optimize farming inputs and outputs. Precision agriculture is farming management concept that utilizes advanced technologies to optimize resource use and improve crop production by responding to field variability, collecting data about the field, analyzing and making informed decisions about where and when to apply fertilizer, water, as well as pesticides. Agriculture is facing numerous challenges including climate change, extreme weather, increasing demand for food. With a shrinking workforce, many agriculture regions are facing a shortage of labor, making it difficult to manage farms and meet production needs. Drone technology overview. Drone types: multi-rotor, stable, fixed-wing, long-range. Fixed-wing drones resemble airplanes, excellent for covering large areas, making it more suitable for tasks like field mapping and monitoring. Multi-rotor drones are ideal for precise applications and close-range work. They are highly maneuverable and can take off and land vertically. There are also hybrid drones, which has combined fixtures of both fixed-wing and multi-rotor drones. They offer vertical takeoff and landing, capable of close-range work while also providing extended range and endurance. Key components include GPS, flight controller, cameras, batteries, sensors, RGB, multispectral, thermal, LiDAR. Data processing tools: Pix 4D, Drone Deploy, and GIS. Applications in agriculture: crop health monitoring, NDVI imaging. Here's an example of that. A farmer in Kansas uses satellite imagery to identify a localized problem in a wheat field, allowing for timely treatment and preventing further damage. Moisture mapping maps cooler, which means moist, and warmer, dry areas in real time, able to identify 3 distinct zones: over-irrigated zones, which is near the slope bases, under-irrigated zones, which is in the higher elevations, and balanced moisture areas. Precision spraying for weeds and plants. A corn farm in Iowa used drones equipped with multispectral cameras to identify weed patches early in the season. The drone mapped the field and generated a weed location map. On a second flight, the same drone sprayed herbicide only on the affected areas, covering 20% of the field. Farmer reduced herbicide used by 65%, saved on chemical costs, and avoided spraying healthy crops, boosting both efficiency and sustainability. Drone seeding in hard-to-reach areas. Irrigation management. Using drones with thermal sensors will detect dry zones across a 100-acre field. The drone creates a moisture map highlighting areas that were dry or over-irrigated. Based on that data, a farmer can adjust the irrigation schedule and flow rates. How drones save time. Fast data collection: they scan large fields in minutes, replacing hours of work. Targeted spraying: apply chemicals where they are needed, reducing waste and crop exposure. Accurate mapping GPS and guided drones create high-resolution maps for soil moisture and crop health. Technical integration framework, workflow, flight plan, data capture, analytics, selecting appropriate drone systems, ensuring hardware software compatibility, farm management system integration, cloud and remote sensing tools. Emphasizing the importance of workflow. It ensures drone integrates smoothly with existing farm equipment software and reduces downtime, data transfer issues between tools. It also enables efficient planning from data collection to action. Example, spraying, irrigation, pesticides. There is also a streamlined workflow, save time, reduce errors, and maximize ROI. Real-time data and decision making. Drones provide live insights on crop health, soil moisture, and pest activity. It enables quick, data-driven responses for irrigation, fertilization, and spraying. This also improves responsiveness and reduces crop loss risks. Implementation strategy. Define clear objectives and KPIs, needs assessment and pilot projects, step-by-step deployment strategy, training personnel in drone application, collaboration with service providers, and performance evaluation. Here are some steps to implement drone technology. 1. Access needs. Identify specific farm challenges such as weeds, irrigation, and crop health. 2. Choose the right drone. Select based on sensors, payload, and field size. 3. Train staff. Ensure operators understand flight planning and data interpretation. 4. Plan flights. Schedule regular flights for monitoring and data collection. 5. Analyze data. Use software to convert drone images into actionable maps. 6. Take action. Apply insights to guide spraying, irrigation, and fertilization. 7. Monitor and adjust. Continuously review results and refine workouts. Drones starting with pilot projects. Test a drone use on small section of farm. Evaluate performance, data accuracy, and ROI. Use these results to refine processes before full-scale adoption of the drone. Cost-benefit analysis. Operational savings 20 to 30% in chemical usage. Initial investment and operational costs. Return on investment estimates. Efficiency and yield increases up to 20%. Long-term cost savings. A cost breakdown of drone hardware. Drone sensors and batteries, software and data tools, mapping, analytics, and image processing subscriptions, training and support, operator training, licensing and technical assistance, maintenance repairs, regular servicing, parts replacement and upgrades, operational costs, labor, charging, and transport for drone deployment. ROI and benefits. Reduce input costs save on water, fertilizer, and chemical through precision use. Higher yields, improve crop health, and early issue detection boost production. Faster decisions, real-time data leads to quicker, more effective interventions. ROI timeline. Many farms see return on investment within 1 to 2 growing seasons. Long-term value proposition, sustainable farming. Reduce chemical use and optimized water management. Improve soil health. Less over-application preserves soil quality over time. Data-driven planning. Historical drone data supports smarter, long-term decisions. Lower labor costs. Automation reduces the need for manual field inspection. And last but not least, competitive advantage. Early tech adoption keeps farms efficient and market ready. Challenges and limitations. Regulatory and airspace restrictions, weather dependence limits flights, skill and training needs, data management and analysis, privacy and ethical issues. There are many barriers to drone adoption, such as high initial cost. Equipment and software can be expensive up front. Training needs. Operators require technical skills and certifications. Regulatory rules. Airspace laws and drone restrictions vary by region. Data overload. Managing and interpreting large data sets can be challenging. Weather depending. Drones are limited by wind, rain, and poor visibility. Legal, environmental, and workforce studies. Legal. Compliance with airspace regulations and data privacy laws can be complex. Environmental. Risk of disturbing wildlife and or ecosystems if not properly managed. Workforce. Requires upskilling or hiring tech-savvy staff for drone operation and data analysis. Case studies of drones in precision agriculture. Japan. Rice fertilizer management with drones. Now let's expand a little bit on that. In Japan, farmers use drones to apply fertilizer on rice paddies. The drones fly low and evenly distribute nutrients based on real-time crop data. This targeted method reduces fertilizer waste, improves crop yield, and saves labor, which is especially valuable in Japan's aging agricultural workforce. Farmers have reported 30% reduction in fertilizer use and more consistent rice quality across fields. Now, how do drones make a measurable impact? Well, up to 30% reduction in fertilizer and pesticide use through precision spraying. Crop yields increased by 10 to 20% in fields monitored and managed by drones. Water usage cut by 15 to 25% with drone-guided irrigation management. Field scouting time reduced by over 80%, improving labor efficiency, and faster detection of pests, diseases, minimizing crop loss and treatment costs. USA, corn pest control using NDVI analysis. Australia, vineyard irrigation using thermal imagery, impact before versus after drone use, and all showed improved yields and efficiency. A future outlook on drones in precision agriculture. Advances in AI and autonomous drones, drone swarm for simultaneous tasks, smart farming, edge computing for real-time decisions, research and policy trends. Advances in AI, smarter analysis and autonomous decision-making. Automation, fully automated flight, that planning and data processing. Swarm drones, multiple drones working together for faster coverage. Edge computing, onboard data processing for real-time insights. There is a lot of ongoing research for using drones in precision agriculture. For example, AI-driven analytics. Drones equipped with artificial intelligence and machine learning are enhancing crop monitoring, resource management, and sustainable farming practices. Conclusion and recommendations. Drones are vital tools for modern precision agriculture. Start with a small-scale trials before full deployment. Drones enhance precision and sustainability. Structured integration is key. Invest in training and system support. Advocate for supportive regulation and innovation. There are many main key takeaways such as drones enhance precision farming through targeted spraying, soil analysis, and moisture mapping. Cost and time savings. There are very significant, reducing input use and improving efficiency. Real-time data enables faster, smarter decision-making on the farm. Challenges will occur, but pilot projects help ease adoption. There are so many long-term benefits including sustainability, higher yields, and competitive advantage. Why integrate drones in agriculture? Well, it boosts efficiency through precise data-driven actions. It reduces costs by minimizing waste and resource use, and it enhances crop health, yield, and sustainability. Before adopting a drone, start a pilot project to test the drone benefits on a small scale. Invest in training to build in-house drone operation and data skills. Support clear policies that enable safe and scalable drone use in farming. Thank you. Here is my references slide, and that is the end of my presentation on integrating drone technology for precision agriculture.